We present an animation reuse method that uses Gaussian processes to generalize modifications an artist makes to a motion. For example, let's say we have this animation sequence and we would like to make the character lean back more. Here the source motion is green and the target, which is an edited version of the source, is blue. Our system learns from this edit and generalizes it to novel sequences. Here we see the result of the generalization. The character is leaning back. We liked the parts of the character walking, but we want to make the character not lean back when he is standing. We can simply correct a small portion of the animation shown here. Our system learns from this correction and refines its internal model. We can run our system again on the same motion. As you can see, the character is leaning back while walking, but not while standing. We can change the walking example to a zombie-like walk. Using this simple substitution, we can make the character walk with his arms extended, like a zombie, in novel sequences. This tool can also be used to animate new characters using already available animations. For example, let's say we have an existing animation sequence and we would like to animate Jack Skellington with it. Jack has different proportions and is likely to move differently than a real person. Traditional retargeting methods may fail or ignore the style of the target character. On the left, we show an existing walking animation mapped onto Jack using traditional retargeting techniques. The artist would like a more exaggerated walking animation, shown on the right. Actually, our artist is a computer science graduate student, not a professional animator. Note the idiosyncratic features in the animation, such as bowed legs. Our system works by developing a non-parametric model of the kinematic and dynamic differences between the source and target, and applying these differences to novel animations. Here, the control character, which is the source motion, is shown in red. This is the motion that is driving our character. Here we have a long motion capture sequence driving Jack. The artist's edits from the example are generalized to this source to obtain Jack walking with exaggerated style. Notice the system reproduces the features of the examples, such as the bowed legs our novice animator created. Now we apply our examples to another sequence which primarily contains skipping. The artist did not provide us with any skipping examples yet. The system detects the lack of examples and falls back to traditional retargeting. However, the artist decides to make Jack skip in a more characteristic style. The artist gives the system an example of how Jack should skip. Now Jack skips like the artist wanted. The artist can continue editing if she is not happy with the result. Our system learns from these edits and will try not to make the same mistakes again. There may be drastic differences between the source and target characters, such as limb proportions, dynamics, and movement style. For example, we expect the giant character to walk slower, with shorter gaits. We also expect the giant to move his weight more during walking, as demonstrated here. From this example, our system generalizes the edits required to take the original character motion to obtain the desired target character motion. Here we have animated the giant by using motion capture to drive him. As expected, the giant character walks slower by shifting more of his weight. Here we show our real-time motion editing environment, where the artist can directly edit an original animation by introducing delta keyframes. These keyframes are layered over the source animation to obtain the target animation. The user can change the dynamics of the animation by manipulating time. We also provide a unique, real-time, full-body inverse kinematic solution that allows the user to manipulate the character interactively. Here the user is changing the kinematics of the motion by dragging joint positions. The goal of our system is to promote animation reuse and provide a directly controllable way to propagate context-dependent animation edits. Let's make the king move. The original motion capture contains walking. Let's make Elvis have a cool strut. Again, the green character is the source training motion. Here's the motion after generalization. As you can see, he struts and moves his head like a pigeon, as in the artist's example. Now let's give him a stylistic skipping animation. Our method generalizes well. This Elvis skipping animation is generated from short walking and skipping examples. The control character, which is driving our method, is shown in red. By learning from the user, our method propagates characteristic features of motion and thus reduces repetitive work in animation.